Hey friends, Dr. Borole is here. Today we are studying unit number 4, that is on instrumentation. We will see various instruments used in electronics laboratories for the purpose of measurement of various quantities. The first instrument and very commonly used instrument in the electronic lab and the measurement of electrical quantities like voltage and current and other parameter is a multimeter. There are two types of multimeters, analog multimeter and digital multimeter. The analog multimeters are the multimeters. They use analog circuits inside for measurement of the electrical quantities. Mostly the analog meters are having analog display. That is nothing but it displays the reading using a pointer on a scale. Whereas digital multimeter, those are also called as DMM. Those are using combination of internal analog circuit plus digital processing circuit. And the output is displayed mostly on LCD screen or LED screen digitally. The common features the multimeters offers are measurement of voltages, that includes AC voltages and DC voltage measurement, measurement of current, that encompasses AC and DC current measurement, and the resistance measurement. Most of the conventional meters, multimeters available in practice, those offers these five features. Whereas some good quality multimeter have additional optional features in them. They are providing measurement of capacitance. They are providing the facility for measurement of temperature as well as measurement of beta of the transistor called HFE. Some multimeters can capable of measuring the frequency of applied signal, and some meter provides auto range selection facility. If you see the diagram of the multimeter that is shown here, you will see this is a LCD display on which the readings are displayed in digital form. There is a parameter selector switch that can select a particular parameter to be measured. For example, here the position of the switch shows off. Then second position is for AC voltage measurement, then DC voltage measurement, then millivolt DC voltage measurement. The next position will be the resistance measurement or capacitance measurement. The next position is a diode testing function or the continuity tester. Then there is a milliampere measurement and ampere measurement. Those are AC ampere measurement. This particular meter is lacking with the facility of DC current measurement. Here there are the connection terminals shown. There is one common terminal, the other terminal where you can connect the positive probe of the instrument in the measurement of voltage or measurement of resistance or diode PN junction testing range. For that purpose, input is connected here. For current measurement, the probes can be connected. The hot probe can be connected either to 400 milliampere connection or it can be connected to the 10 ampere terminal. The another multimeter shown here, in which you will see again there is a range selector, there is a LCD display, and there are connection terminals. In this meter, you will see the range of measurements of DC voltages, in which there are various sub ranges are there: 200 millivolt range, 2000 millivolt range, 20 volt range, 200 volt range, and up to 1000 volt. The 200 millivolt range means whenever you apply the voltage to the input terminal, that voltage should be in the range of 200 millivolt, and the meter can display 200 millivolt on the display. That is the maximum. If your input voltage is more than 200 millivolt, then probably you have to select the range of 2000 millivolt. If your range is more than that, then you can go for the higher ranges. If you apply the voltage to the meter which is higher than the range selected, then out of range indication is displayed by the multimeter. That is 1.000. That indicates the out of range. The third meter shown here, that is an analog meter. Again, it consists of a range selector as well as the connection terminals. Whereas it uses the analog meter that is marked with the dial, and the pointer is used to display the reading on the selected scale. The basic block diagram of the DMM is shown here. We have already discussed that multimeter can be used for measurement of DC voltages, DC currents, AC voltages and AC current, and resistance. Let us see how these measurement can be done by the internal circuitry of digital multimeter. So digital multimeter block diagram is shown here. The input terminals are shown here. Those input external parameter can be connected, that is either voltage or current, that can be connected to through input probe to the input terminal. There is a rotary selector switch as we have seen on the front panel, which allow you to select a particular parameter measurement, that can be a resistance measurement or AC voltage measurement or AC current measurement or DC current measurement or DC voltage measurement. Here there are some blocks like calibrated attenuator is shown. This calibrated attenuator is basically providing you the multiple ranges for measurement. For example, here AC voltage measurement, there is a block calibrated attenuator. This calibrated attenuator provides you the ranges of AC voltage. For example, 200 millivolt, 2000 millivolt, 2 volt, 20 volt, and so on. Similarly, there are some blocks current to voltage converter. Those are normally used for measurement of current. Normally, in case of current measurement, the input applied such that the meter can receive the current. That is, basically the meter is inserted in series with the component so that the current flowing through the component is also flowing through the meter. In this measurement operation, the current is allowed to flow through a circuit which converts the current into voltage. And for that purpose, current into voltage converter block is normally employed. And converted voltage is then connected to a analog to digital converter. Because up to this level, the voltage handled by the digital multimeter is analog in nature. If you want this digital display, then you have to convert this analog voltage to the digital value, binary value. And this binary value will be then displayed on the display after converting it to the appropriate code, normally 7-segment code. And therefore, digital code converter is basically a 7-segment display code converter. It depends on what type of display you are having. If it is LCD display, then a appropriate digital code converter can be employed which can drive the LCD module. We will see further how the individual parameter like DC voltage, DC current, AC voltage, AC current and resistance can be measured using this block diagram. So we will redraw the block diagram in a particular case and then we will see how the parameter can be measured. Let us see the first parameter DC voltage measurement, in which let us see whenever the switch is in DC voltage position, that is the position number 5. What circuit is in picture? This input is now applied to calibrated attenuator and then it is going to analog to digital converter and then it will be displayed on the display unit which is driven by the appropriate LCD display driver as well as port converter. The same circuit is redrawn here. See here, input, external input which is to be measured is applied here to the input. The common terminal is connected to the ground input or common input and positive terminal is connected to the positive terminal of the multimeter. The multimeter will be switch in DC voltage measurement range. Then first block coming in series will be a calibrated attenuator. Function of this attenuator is to attenuate the input level to the output level required, which should be demanded by A to D converter. A typical value, for example, analog to digital converter requires say 0 to 5 volt input to display the reading from 0 to full scale. Then from minimum to maximum input value, the output of the attenuator should be 0 to 5 volt. This can be done by using the calibrated attenuator. For example, if your input voltage is changing from 0 to 200 volt, then this calibrated attenuator will provide the voltage division function and it will calibrate the output of the attenuator such that for 0 to 200 volt input, the calibrated attenuator output will show 0 to 5 volt. Analog to digital converter then converts this 0 to 5 volt to the binary value from 000 to maximum digital value which is displayable by the display unit. And display unit, code converter and display unit directly displays this value on the display. So for 0 input, calibrated attenuator output is 0, ADC output is 0 and the display will display 0 output voltage. When the input voltage is maximum to say 200 volt, then calibrated attenuator output will be maximum to 5 volt. A to D converter output is also goes to the maximum value, that is all bits of the outputs are 1, and when it is displayed, the display will show the maximum displayable value, that is 200.0, that is 200 volt. Now second parameter measurement, AC voltage measurement. The block diagram, if you see now, the input is applied to the input terminal. The rotary switch which select the AC measurement function is connected to AC volt position. The calibrated attenuator is coming in series which provides the calibrated output for the given value of the input. Addition to that, we know the output of the attenuator is now AC signal, whereas our analog to digital converter needs the output which is in DC voltage form, and therefore we need to convert this AC output to the DC value or average value by using rectifier circuit. The rectifier also includes a filter circuit so that the average value of the AC voltage can be connected to ADC. Also, in this chain, there is a calibration constant that can be added so that Whenever average value is converted by analog to digital converter, this value should be such that it is corresponds to RMS value of the AC voltage applied. Function of analog to digital converter is to convert the analog average DC signal is now to a digital value, and display unit again displays it on the display module. So this way AC voltage is measured. The next parameter is AC and DC current measurement. First we will see the DC current measurement. Consider here the block diagram. Now the meter is connected in series with the component in the current path so that the DC current can flow inside the circuit. Let us suppose that we are going to measure the DC current, then this switch will be switched to position 4, that is DC current position. Then the block comes in series with this current is current to voltage converter. This current to voltage converter will convert the current to the appropriate voltage. This output of current to voltage converter is calibrated in such a way that it will again provide the output, that is a full range output for analog to digital converter for full range input applied. What it means? It means that let us suppose that you have selected the input range 0 to 400 milliampere. Then for 0 to 400 milliampere, this current to voltage converter will provide you the output 0 to 5 volt. 0 to 5 volt then converted by ADC to binary value 0 to all bit 1, and that indicate the maximum reading on the display, that is 4000. Whereas for AC current measurement, the connections are same, only you have to change the range from DC current to AC current measurement. What comes in series of the current is now current to voltage converter, but the output of this current to voltage converter is now proportional AC voltage. This AC voltage is then converted to a proportional DC voltage by using rectifier and a filter circuit. And then average DC value will be applied to A to D converter. Then further section will display it on the display. A typical current to voltage converters are shown. In the simplest form, current to voltage converter is a resistance. Let us see, this is the current I. When this current is allowed to flow through the resistance, it will produce the voltage across it. And that is nothing but V is equal to IR. And therefore, simple circuit converts current into proportional voltage. The proportionality constant is the resistance R. If R is of 1 ohm, then output voltage V is coming out to be 1 into I, and that is nothing but I. So output voltage V is directly equal to the magnitude of the input current. And then this voltage will be further given after a calibrating circuit to analog to digital converter, and further it will be displayed on the display unit. The another current to voltage converter using operational amplifier is shown here. We have already studied the operational amplifier in the first chapter. Now if you see this circuit, this is nothing but inverting configuration of the circuit. The input current is now applied to the inverting terminal and non-inverting terminal is grounded. When non-inverting terminal is grounded, the inverting terminal voltage also becomes same as the ground voltage. The concept behind it is called virtual ground concept. So whenever input current comes to the inverting terminal, that is at zero potential, this current finds two paths. One is going through this feedback resistance Say let us say R1 is in the circuit now, and another path is through the operational amplifier input terminal. But we know the operational amplifier input resistance is very high, ideally infinite, and therefore no input current actually flowing through the op amp. So whatever current comes to inverting terminal, that will leaks through the resistance R1, which produces the voltage drop across R1 that is shown here. And this voltage drop is same as the output voltage. The resistance R1 is selected such that the current to voltage converter will provide the calibrated output. That is nothing but for minimum to maximum change in current, the output voltage of current to voltage converter also changes from minimum to maximum, that is required by A to D converter to display the maximum reading on the display unit. The next parameter measurement is a resistance measurement. How resistance is measured? Up till now we have seen that these three blocks, analog to digital converter, code converter and display units, they are responding to DC voltage and displays the DC voltage connected to analog to digital converter. In resistance measurement, we will convert the unknown resistance connected to the multimeter terminal to a proportional voltage. And then that voltage will be measured, and this voltage is calibrated in terms of resistance values, and therefore the display value will be directly in terms of resistance in ohm. Let us see. This measurement consists of a current source, the switch which selects the parameter will be in the resistance position. So this current through the constant current source, the name itself indicate constant current source provide the constant current output. Let us say it provides 1 milliampere constant current output. When it flows through the unknown resistance R, then it will produce the voltage drop across that resistance with top end positive and bottom end negative. And that voltage is nothing but V is equal to IDC into R. For example, if R is of 1 kilo ohm and IDC is of 1 milliampere, then voltage across the resistance is 1 milliampere into 1K. That is nothing but 1 volt. This 1 volt is connected to a buffer amplifier. Buffer amplifier is simply an amplifier which provides very high input impedance so that the meter should not provide the paralleling effect on the unknown resistance. Normally, this amplifier have unity gain. So, buffer amplifier output will be same as the input connected to the buffer amplifier. This is then connected to analog to digital converter, and that will display that voltage on the digital display. Whereas the voltage is already proportional to the resistance, and therefore whatever the reading displayed by the meter is directly showing the value of resistance in ohm. This way the measurement can be provided. The another equipment normally used in electronic laboratory is a function generator. Function generator, the name itself indicate that it can generate the various signals called functions. Typical functions, the function generator can generate are sine wave, square wave, triangular wave. The block diagram of a function generator is shown here. There is a selector switch at the output and three output available from the function generator. This selector will select one of the function or waveform connected to the output terminal. So by selector switch in the square wave position, you will get the square wave out. The selector switch is in sine wave position provides the output voltage which is sinusoidal in nature, and the selector switch in triangular position provides the triangular wave as a output as shown here. In addition to that, the function generator have facility to change the amplitude of the waveform, and there is a facility for controlling the generated waveform frequency. Some function generator additionally provide the facility to change in the duty cycle of the waveform. The duty cycle control is applicable to square wave function only. When the duty cycle is defined as on time to the total time period of the signal. And on time is nothing but the time for which the output will be in high state. Let us call it as T on, that is this period. And total time period is the time required for one cycle of the square wave. So we can able to change the on period here, keeping total time period constant. So whenever on period is 50% of the total time period, then duty cycle T on by T is 50%. When on time is lesser than 50%, then duty cycle is less than 50%. That can be adjusted by a knob provided for duty cycle control. Similarly, we can increase the on time much higher than the 50% of the time period, then duty cycle is higher than 50%. The duty cycle control practically provides the duty cycle change from around 1% to 99% of the time period. Whenever you are using the duty cycle control, that also affects the other waveform. They will getting distorted, and therefore normally while generating and using triangular wave and sine wave, we should keep the duty cycle control off. The front panel controls of a function generators are shown here. It is having a display unit that is directly providing the display in terms of digital reading. Old instrument function generators can have the analog pointer type of display also. But nowadays, most of the instrument have digital display that can display a particular parameter. It is having a selector switch to select the function sine wave, triangular wave or square wave in the form of selector buttons. It is having a switch to power on and off the instrument. Whereas it offers the range of frequency generation. So the frequency, total range of frequency can be divided in sub ranges like 0 to 1 hertz or 0 to 10 hertz or 0 to 100 hertz or 0 to 1 kilohertz, or it is 10 kilohertz or 0 to 100 kilohertz or 0 to 1 megahertz, like that. So whenever you select the particular range, then in that selected range, the frequency can be changed by using a analog dial. This can provide you the change in frequency from 0 to maximum of the selected range. So by changing the position of this dial, which is basically a potentiometer, then by changing this position, you can able to change the frequency generated by the function generator. There are the terminals provided for output connection. Here a BNC connector is normally provided to connect the generated signal to the external circuitry. And this function generator also provides a knob for change in the amplitude. So this knob provides to change the frequency of generated waveform, and this second control knob provides a amplitude change. The optional features the function generator can provide is the duty cycle control features, a triangular wave slope control features, and some function generator can provide the modulated output called amplitude modulation and FM modulation output. A typical block diagram of a function generator is shown here. Whenever a DC voltage is applied to the integrator, the integration of a constant is a ramp. When the DC voltage is alternates from positive to negative, then the ramp output of the integrator ramps up and ramps down. That is nothing but a triangular wave. This triangular wave is connected to a Smith trigger circuit. Smith trigger circuit will convert the triangular wave to a symmetric square wave. Similarly, same triangular wave can be available as a output, and same triangular wave will be given to a sine wave converter, which is basically clipping the peaks of the triangular wave via a wave shaping circuitry. And this after wave shaping by sine wave converter, the output of the sine wave converter is a sinusoidal waveform. It is connected to a three position switch. This position switch can select the appropriate waveform. That is further connected to a calibrated attenuator that will provide you this range selection as well as the output frequency control. Simultaneously, the amplitude of the output can be changed by changing the integrator charging parameters by using a frequency this charging current control circuitry. So therefore, output of the attenuator now is a function you have selected, and the waveform will be decided by the switch, which is either in square wave position or in triangular wave position or in sine wave position. This way, the function generator generates the various waveforms. Those waveforms can be used for testing purpose in electronic lab. That's all, friend, for function generator. So we will stop here today. Tomorrow we will see the next instrument. Till then, bye bye.